Excellent. All right, welcome everyone to today's Delegate Assembly. Today we have two contributed talks, one from Dan and one from Antonio, both based on DP0 related data. We're just having a couple of announcements this morning. One of them is a reminder that the Data Preview 0 virtual summer school is coming up in June. This is good for delegates who've been around for a while, who maybe want to go back and relearn some skills or do some networking or some co-working. And it's also great for students. So if you're thinking about having a student come in for the summer and maybe do a DP0 related project, send them to the virtual summer school. That'll give them an accelerated learning experience. That's going to be June 12 to 16, and the link there for more information is on this slide. You can still see the slide, right? I lost the green border. Yeah, okay, good. Second announcement is as just another reminder that the Rubin 2023 project and community workshops coming up in August. It's the 7th to 11th. It's going to be in Tucson again this year, but it's going to be in town, like right next to the university. The meeting website is there. Registration is not quite open, but we are taking suggestions for session topics for breakout sessions, and also contributed abstracts for talks and posters. As a final reminder, there is space in upcoming delegate assemblies to present. You can present anywhere from 10 to 15 minutes, right up to 50 to 60 minutes, sort of whatever you've got. We'd love to hear about it. So consider if you might want to present something. Work in progress is always welcome, and just reach out anytime. So today we're going to have two talks. These are presentation style talks, so you don't need to be logged in to the Rubin Science platform. You don't need to have any particular notebooks open in order to follow along today. So it's kind of more of a regular style. We're going to start with Dan. He's going to talk for about 30 minutes, and then we're going to have Antonio for 15 minutes, and each of them will get a 5-minute warning from me as they go. There's, as always, there'll be time for questions at the end. The chat is open, so if you post questions as we go, I can interrupt the speakers on your behalf to ask questions. I can see everyone, so if you use the raised hand feature, I will always also be able to see that, so we can do questions as we go. And then afterwards at 10 a.m., as per usual, we will have general Q&A here in the main room. If you're working on DP0 and you have questions for Rubin staff, we'll be here, and we'll try to set up some breakout rooms for topical co-working as well. So all that happens as normal. All right, let's do it. I'm going to stop sharing my screen and invite Dan to start.
That's great. Thank you very much. Sorry, just move the Zoom controls out of the way. Okay, yeah. So hi everyone. Thank you for inviting me to give this talk. So basically, I'm going to be talking about some of my work that I did as a. Sorry, I'm going to be talking about some of the work that I did in my PhD, which I just finished last year. I'm now a postdoc at the University of Birmingham in the UK, and this presentation is going to be on a cluster finding method that I developed with the motivations for finding lens transients in upcoming wide field surveys such as LSST. Sorry. Okay, so I just thought I'd give a brief overview about gravitational lensing. I'm assuming not everyone is a gravitational lensing researcher, so I thought I'd start with this. So here we have a background galaxy, and normally the only way that light can travel from the galaxy to the observer here on Earth is through a straight line. However, if there's something of significant mass in the way, for example, in this scenario here, there's a galaxy cluster in the way, then the light will be bent, and you can actually create multiple paths that the light travels on to reach us here on Earth. And the consequence of this is that it produces multiple images of the background galaxy. This has a few other consequences, such as the time delay that happens between the arrival of the two images means that we can measure things such as the Hubble constant. The background images of the galaxies are distorted and sheared, and they can also be magnified, which is useful for essentially acting as a free upgrade to our telescopes. It allows us to see things that are more distant than usually would be possible. And just adding in the time delay that I was explaining earlier comes from two main components. The first is that the length of the paths that the light takes forming the different images of the background object are different, which causes the light travel time to vary. And also you get varying amounts of time dilation from the photons as they pass through different levels of the lens's potential. So strong gravitational lensing is a regime of gravitational lensing where the light passes close enough to the lens that it's distorted into multiple images, as I've mentioned before. This is normally quantified by the Einstein radius of the lens. So as you can see here, there's a galaxy which has been distorted into a few multiple images in an arc-like fashion. This is the usual structure that we associate with gravitational lensing. And with this Einstein radius, you can quantify a kind of strong lensing cross-section. So this is the area within a background source needs to be in order to be strongly lensed by that object. On the right-hand side is an example of a galaxy cluster lens. As you can see, there's multiple arcs here caused by the much larger strong lensing cross-section of the galaxy cluster, and the arcs appear at different radii because the sources are at different redshifts. And typically we have these two kinds. Oh, sorry, I didn't mean to go on yet. So typically there are two kinds of lenses. We have isolated galaxy lenses, which are typically lower mass and have lower Einstein radii, and galaxy cluster lenses, which are higher mass and have larger Einstein radii. And this is an example of a galaxy cluster lens model, which has, so the reason I'm showing this is because the strong lensing cross-section, which is roughly approximated by the red lines here on this image, is very elongated and much more irregular than, for example, with the single galaxy lens. So there's quite a range of different lenses that exist. Okay, so this presentation is mainly on the lensing of transients. So when I'm talking about transients, I'm talking about any phenomena which change in brightness over some kind of rapid time scale. For example, supernovae and gamma ray bursts are examples of transients that we'd discuss in terms of photons. And then obviously we have gravitational waves, which are still considered transients, even though they have nothing to do with emission of photons. And then, of course, the kilonova counterpart of gravitational waves. So lens transients happen when the host galaxy is lensed, and when the sorry, I just lost my train of thought. So when we have a lens background galaxy, if there's a transient that goes off in that background galaxy, then the same transient will also be lensed. There's a couple of examples on the right-hand side here. So the bottom one is a very famous example of supernova Refstau. So this was a supernova that went off in a background galaxy that has been lensed 3 times. You can see there is one image up here and then 2 images here closer to the center of the cluster. And the supernova went off in this background galaxy and appeared 4 times in an Einstein cross configuration here, labeled as S1 to S4. And then it reappeared again at a later date in this other image of the galaxy in the background at position SX here. This was predicted with lensing models to a fairly good precision. The top image here is also another lens supernova, but this is one which was lensed by a relatively small galaxy, as opposed to the supernova Refstal on the bottom, which was lensed by a galaxy cluster. And I bring this up just to show the differences in the scales of images produced by gravitational lensing. So you can see here, this is much smaller than even an arc second, whereas the images of this background galaxy here are separated by a few tens of arc seconds. And as I mentioned before, the time delay of the arrival of the images of the supernovae can be useful for measuring cosmological parameters like the Hubble constant. This is especially true for type 1a supernovae, which are very easy to, or easier to measure the magnification with due to their standard candle nature. So I mentioned that this presentation was to do with galaxy cluster finding. So what has this got to do with lens transients? So I think the first thing to start off with is that this plot here is showing that approximately 50% of all high magnification gravitational lensing is done by galaxy clusters. The other 50% is done by galaxies. So this green and blue line here is showing the optical depth to strong lensing. Essentially, it's just the fraction of the sky which is strongly lensed. And you can see that this distribution between 10 to the 12 solar masses and a few times 10 to the 14 solar masses is relatively flat. So the contribution is roughly equal between galaxies and clusters. A lot of people tend to focus on lensing from single galaxies, mainly because their lens distributions are more simple. But if we're just interested in the discovery of many lens transients, then we need to also include the contribution from clusters as well, because they are significant. Also, looking for lensed objects in general is very difficult. So we're looking at things, as I've shown before, on small scale, so it requires very high resolutions. A lot of the sources that are lensed, even though they're magnified, can still be very faint because they come from very high redshifts. And it's also a very rare phenomena in that it requires a very precise alignment of a background source with the lens. So one thing you can do is you can significantly cut down on the search region by concentrating on known lenses. So essentially lenses which have galaxies within their strong lensing cross-section, and we can see those lens galaxies in the form of multiple images or gravitational arcs, and just look for transients that go off within these lens galaxies. However, that doesn't cover all the possibilities that can happen in terms of lens transients, because the requirement to discover the lens background galaxies in the first place is a function of the observation depth of the survey that you're using to discover these lenses. What this plot on the right-hand side is showing is if you had a big list of galaxy clusters made up by the fact that they have lens galaxies behind them, how many of those clusters, how many galaxy clusters in the universe would you be missing out on if you went by the fact that a lot of them just don't have observable galaxies behind them? And even at very high observation depths, we miss a large fraction of these galaxy clusters, even at depths such as with Rubin, which is on this plot somewhere between the 24th and 25th magnitude, so somewhere between the green and red lines, especially for masses of about 10 to the 14 solar masses, which is very typical for galaxy clusters. And so because of this, we can have the situation where we don't see the background galaxy, but we can still see the lens transient. So these transients are detected as hostless transients. And hostless transients is something that happens fairly often, again, because the supernova can be brighter than than its host galaxy, so it can be discovered first. And also in cases of things like gamma ray bursts or gravitational waves, you detect them completely independently of the way that you detect the galaxies. So this plot here is showing the fraction of galaxies that, the fraction of transients which are detected as hostless with current limits, such as using the dark energy survey, and given that the lens transient distribution peaks at somewhere between redshift 1 and redshift 2, so somewhere between these two lines, approximately 15 to 50% of all transients are considered hostless. So what this means is that if we can detect the transient, but we don't detect the galaxy, then we wouldn't necessarily know to look near that galaxy cluster that's lensing the background galaxy, because we haven't observed the background galaxy itself. So therefore, we need to adopt a slightly different strategy in searching for these lens transients. And that is to look near essentially any galaxy cluster that we can find. So this is why we decided that it would be a good idea to develop a new cluster finding tool in order to find these clusters and enhance our probabilities of finding a lens transient. And of course, you might be asking that many cluster catalogs already exist. Why do we need to bother making a new one? So this is a perfectly reasonable question, and there are reasons for this. So for example, possibly the most sensitive cluster catalog out there is RedMapper, and this uses photometric SDSS data, which means it's only limited to finding clusters within the SDSS footprint where this data are available. In addition, this is mostly in the north, which has bad synergy with wanting to find lens transients with Rubin. Ideally, we'd want this catalog to be full sky. Other common cluster catalogs involve clusters that are detected through X-rays and through the Sonia-Zeldovich effect, but these cluster catalogs are typically too sparse and don't include a large number of clusters that we would require for our searches. So we opt for, similarly to RedMapper, we opt for optical or infrared detection of galaxy clusters. Another question you might ask is that, of course, LSST itself will find many new galaxy clusters. So why should we not wait until LSST comes online and all the new clusters are discovered, and go from there, because the sensitivity will be unprecedented and we'll discover so many new more clusters that way. Well, the problem with that is that you're essentially wasting time that LSST is online for. So if we can discover the galaxy clusters before LSST comes online, then we can enable early science in the first years of the survey. In addition, LSST is also limited to the south. So if we can figure out the way to, this way to find these clusters, then we can increase the scope to the Northern Hemisphere as well. So, the main data set that we used is J-band data, J-band photometry, in order to detect the galaxy clusters. So the reason for this is that this is essentially the only photometry that exists that covers the entire sky that can detect an L-star galaxy, so a typical galaxy in a cluster, out to a sufficient redshift that covers the ranges that we were interested in for the lensing of transients, so out to about redshift of 1. So this all-sky data already exists, and this is shown on this plot here, which is showing the distribution, the color magnitude evolution of a L-star galaxy in the J and WISE-1 bands, and both of these bands are sensitive enough sorry, the data that exists in both of these bands is sensitive enough to detect an L-star galaxy out to redshift of 1. So these dotted lines here are showing the depth of the surveys. The problem with the WISE band is that, unfortunately, the PSF is too large for us to get accurate photometry in cluster cores where the galaxies themselves are very close together, and so you get a lot of blending, and the photometry doesn't quite match up with our expectations. As you can see with these examples of images here from VHS, you can see that you can see the distribution of the clusters in the the galaxies in the cluster a bit more clearly than in WISE, where you can see the PSF has blended a lot of them together. So the photometry isn't quite as accurate with WISE. In addition, it's not precise enough for us to determine colors. So this is why we're really only limited to using the J-band data, although we can use the galaxy information from WISE as verification to confirm that the objects that we're looking at certainly are galaxies, just because they're detected in both bands. Okay, so we essentially only have one photometric band or sky. So how can we use this to detect galaxy clusters? Well, we use a technique called wavelet filtering, which is very simple. It just starts with a raw map of galaxy positions. So for example, this this red pixelated plot on the left-hand side. And then we convolve that with a kernel, which has a particular functional form. So this one is a difference of two Gaussian functions. So it has a narrow but tall positive Gaussian component, and then a negative, which is shorter but wider. And this, when you convolve that with the pixelized galaxy map, it produces a smooth density map of the galaxies, which is what's shown on the right-hand side. And we can use these maps, these density maps, to extract the clusters from. So this is an example map, which contains a known galaxy cluster that we used for testing. The peaks in the map are where clusters can be extracted from. So you can see in the center, the white plus is marking the position of the known galaxy cluster, and you can see there's a big bright peak right next to it. So that galaxy cluster has been extracted. And then there are also some auxiliary clusters that you can see, which aren't quite as massive, and so their signal that they produce is not quite as strong. But either way, they're picked up by the cluster finder. And for each of these peaks, we define a signal to noise ratio, which is quite similar to sort of like a bootstrap sampling procedure, in which every time we create a map, you can say, let's randomly distribute all of the galaxies in this map, and what would be the probability of getting a peak of the same size if all of the galaxies were just randomly distributed. So this gives you a way of picking out the signal of the galaxy cluster over the background of randomly distributed galaxies. And we use a cutoff of 3 for the signal to noise ratio to as a cut for the candidate clusters.
Dan, can I ask a question about the making the maps?
Yes, of course.
Yeah, and your cluster finder. So those Gaussians, like the difference of the Gaussians that you use,
yeah,
is the size of those, is it like related to the size of the clusters you're expecting to find? And do you do it for like different redshift bins?
Yes, so the inner Gaussian is tuned to the typical size of the galaxy cluster core. So it's just under an arc minute. I can't remember the exact value. But yeah, the size is tuned, and we experimented with changing the size based on different redshift bins. But the problem is, because we only have a single band of data, we don't really have any redshift information about the galaxies. So it's very difficult to constrain which galaxies are in which redshift bins.
Okay, that makes sense. Thank you.
Okay, so this is the role of DP0 in this whole procedure. Obviously, DP0 provides us with a very unique opportunity to be able to test the cluster finder on a data set where we know what the distribution of the galaxy clusters, or in this case, the dark matter halos, are, their masses and their positions. So the one problem with this is that the LSST bands are not exactly the same as the infrared J band data that we've been using before. So we select the galaxies in DP0 to be as close to this as possible. So we use the reddest band, the Y band, and we cut off the data to be similar observational depth than is that we have with our J band data, and we keep everything else the same, and we just run the cluster finder on the DP0 data and see what the results are. So this is showing a particular part of the DP0 field, which has a very large galaxy cluster at the center of it, which you can see is picked out nicely by the method. So in this particular example, the pluses are the locations of all of the dark matter halos of 10 to the 13 solar masses or greater. And hopefully you'd agree with me that qualitatively it looks like the cluster finder is working in the peaks are near the distributions of these dark matter halos that are dotted around. And all of the peaks in the map have at least one of these dark matter halos associated with them. And by that, I mean that the separation between any peak and a dark matter, and at least one dark matter halo, is 1 arcminute or smaller. So this was a very encouraging test to see that in this case, the cluster finder seems to be tracing the distribution of the dark matter halos in the simulated data. The other thing that we did was we were able to test the recovery fraction of the clusters as a function of their halo mass, because we know what the halo mass of each halo is in the simulation. So we looked at how many clusters were recovered in the simulated data as a function of the minimum halo mass. So we said, let's include all galaxy clusters from a minimum halo mass upwards and see what fraction of those get recovered. So above 10 to the 14 solar masses, we essentially recover all of the halos. As you can see here, it plateaus, which is very nice. Obviously, as we start adding more halos and ones of smaller mass, then they have less galaxies bound to them, and it's harder for the method to detect. But with our signal to noise ratio at 3 cutoff, we fall below 80% at approximately 7 times 10 to the 13 solar masses, which we were relatively pleased with, given that our main expectations was that we wanted to detect clusters of approximately 10 to the 14 solar masses. And I forgot to say that our what's the word I'm looking for? Our condition for whether a galaxy cluster was considered or a dark matter halo was considered as recovered was just to look at the peaks and to see to look at the halos and see if there was a peak within 1 arcminute of that halo. So that's how this plot was produced. So we also did some performance tests on other data that wasn't DP0. So I'll quickly go through that as well. So we tested it on some data of known galaxy clusters, or some regions of sky which we knew contained galaxy clusters. This plot on the left here is showing the the signal to noise that was produced by the method as a function of their Einstein radius. It's unsurprising to know that the large Einstein radius, or the large mass clusters, produced a much higher signal to noise than those of low mass. And as you get to the lower mass clusters, the recovery fraction starts to drop. So we essentially recover all of the large Einstein radius clusters and recover approximately 60% of the lower Einstein radius clusters, which is summarized with this plot on the right-hand side. And we also tested the false positive rate by looking at some data with CFHT lens, which provided photometric redshifts for many of the galaxies nearby some massive clusters. So we were able to match up the CFHT lens galaxies with our infrared galaxies and look for photometric redshift peaks in the outskirts of the main galaxy clusters that the CFHT lens data were collected for. So this allows us to look at some peaks that are not necessarily associated with the main galaxy cluster, and to check whether these, and to use the photometric redshift information to check whether these are real galaxies or not, just by looking for overdensities in the photometric redshift histograms. So for example, this one here, you can see there's two peaks on the histogram here. So given that there's peaks, we assume that this is a real galaxy cluster, given that there's a large overdensity of galaxies at a given redshift. And this produced results of approximately 6% false positives if we take the signal to noise ratio cutoff to be 5, and if we take it to be 3, then we get more false positives at 17%, but this provides us with about 4 times more detections. So it's a trade-off for more false positives, but more detections in total. Okay, so that essentially wraps up the main bulk of the presentation. I just wanted to talk about some future steps that we're going to be looking at going forward. So something that I'm doing whilst also juggling other projects is trying to optimize this algorithm for the full sky cluster search. So we've established the method, and we're pretty confident that it's going to give us some results that we're happy with. So now I'm working on optimizing this and actually creating the catalog that we're going to use for the future. I'm going to be doing some tests against the large cluster catalogs that exist, such as RedMapper, and compare the rates of detection and false positives, things like that, to see if there's and to use the detections of clusters in using other methods to verify the detections that we make in our method. Of course, to use these catalogs in searches for many optical transients, especially with LSST, looking for things like supernovae and lens supernovae and lens kilonovae, and also other flavors of transients such as gravitational waves and gamma ray bursts that won't be detected necessarily with Rubin, but will be detected with other instruments, the LIGO instruments, SWIFT, for example, in terms of GRBs. And there's also some additional work that I'd like to do using the DP0 data in preparation for LSST. So, for example, how useful is this method going to be for finding clusters during the survey? Does it perform much worse or much better than other cluster finders that will work with the LSST data? How can we improve the method using multiband photometry and with photometric redshift of the galaxies? Just to investigating how this additional information that we'll have over such a large patch of sky will improve the cluster detection rate. Okay, thank you. I think that's everything I want to talk about. So I think I'll just leave my conclusions here, and if anyone has any questions, I'm happy to answer.
Wonderful. Thank you, Dan. Round of applause for Dan. Yay. Thank you. And we do have time for a couple of questions. I had one. When you were talking about how you sort of take the Rubin images and then you run the kernel on it, that can be like pretty computationally intensive. And I was wondering if you can you bin the images first?
Sorry, what do you mean by binning the images?
Like to cut down on the number of pixels, the number of calculations you're doing when you do the kernel convolution. Can you bin first since you're degrading the resolution kind of anyway? Can you
Right,
bin
yeah.
the image?
So that does happen when I if I just go back to this pixel grid here, I bin all the galaxies so they're in a specific resolution of pixel.
Oh, do you start with images or do you start with a catalog that then you put down a grid?
Yeah, we just start with the catalog. So we just take
Oh.
the coordinates of the galaxies and go from there. So yeah, we don't need to process any of the imaging.
Okay. Okay, cool. That is much less computationally intensive.
Yeah.
Yeah. Okay. Bob.
I hope this isn't too tangential, or but fundamentally, I know that you can measure the Hubble constant with time delays, but I've never found out how. And I was wondering if there's a short explanation.
Sure. So the way that I think of it conceptually is that maybe this isn't right. Maybe someone will correct me. But the way that I think about it conceptually is that you receive one image of the background source at some time, and then you receive the second image at a later time, and obviously there's some time delay between the two images arriving, and you should be able to calculate the travel time of light in both cases. But then there's an additional factor in there that delays the arrival of the second image compared to the first one, and that is the expansion of the universe. So as long as you can precisely track down all of the other parts of the delay that go into it, then the only thing that you don't know is the part that's influenced by the expansion of the universe. And so you use that to calculate the Hubble constant.
That's a good start. I appreciate it.
Thanks, Bob. Douglas?
Oh yes. So very nice talk. This sounds like really this looks like moving this into the Rubin era will be really nice, especially there's there'll be a lot of overlap with like the SPT data set, and I guess in the future the CMBS4. I know for a historical fact, the dark energy survey was actually originally planned as a survey to get photometric redshifts for clusters that were found by the South Pole Telescope (SPT) using the integrated Sachs-Wolf effect. And do you eventually plan to cross correlate with SPT or other southern? With moving ahead, looking ahead for the Rubin era, do you plan to do cross correlations with these various radio and submillimeter experiments?
Sure. I mean, I don't know a huge amount about these cluster catalogs. From my experience, the number of clusters that you get from these techniques is much lower than you get from the optical techniques that, for example, RedMapper uses.
Mm-hmm.
So it tends to be a lower priority just because there's fewer things to match in, and we're interested in finding as many as we can. So we're really looking at the catalogs which have very high numbers of clusters within them.
Okay, Lee, thanks.
We'll do Louise and then we will switch.
Thank you for the presentation. It's really amazing that you can get a cluster catalog with one band. I guess, do you have, I mean, you don't have any redshift information. And do you have an idea of how many of your clusters are like superpositions of clusters, one in the foreground, one in the background?
So yeah, as you said, we don't really have any information or any good information on redshift. We can try and do photometric redshifts with the Ys, but as I said, it's not really precise enough to give us any accurate information. I don't have a good number in my head for how many clusters are superpositions of multiple, but also for my work, I don't really care, because what I'm really interested in is looking for really high density lines of sight that will contribute strongly to gravitational lensing. So if there's multiple galaxy clusters along the same line of sight, then they're just going to add to, produce higher density lines of sight in that region, and that gives a high probability of lensing in that region. So that's what I'm mostly interested in.
Thank you. Jeff, we do need to switch. Can you put your question in the chat for Dan?
Yeah, no problem.
Yeah, okay, thank you. Okay, thank you very much, Dan, again. Thanks for being here and for giving the talk. That was excellent.
Thank you very much.
Very interesting. Antonio, you're up.
Right.
Go ahead and share your screen. Take it away.
Yes. Okay. So, hello everyone. My name is Antonio Vanzanella, and I'm a scholarship holder at Parthenope University here in Naples. And today I will present my notebook named Detection of Slow-Moving Object with LSST. And we aim to build a machine learning pipeline to detect slow-moving objects such as long-period comets. And to do so, we want to build and represent these samples, and that they represent the main feature of this object, so they should appear faint and slowly. Thus, to translate these we translate these into a dataset of a sequence of frames where the object moves, and of course we build our machine learning model as a result of that. So in this notebook, I show how to retrieve and collect a series of cutouts from a sequence of images, and at the same sky coordinate ordered by time. And then I'll compress them into archives and giving some insight on how we use them to build a dataset and how we use them to train a CNN, in our case, a 3D CNN. So the original version of the notebook, the whole notebook, could be put in a for loop, since we want to create a great amount of samples, since a machine learning.
Antonio,
Yes.
can I interrupt you? Can you make the font a little bit bigger? I have a really big screen, but I think others might. That is better. Yeah, thank you.
Okay. So I was saying that we put this in a for loop to build our dataset, and in this way we make a lot of samples. But today I will I split all the notebook in small code fragments, and we will see step by step. First of all, we imported the libraries and the Python package to process the data, so the LSST package and the other package to interpolate the data and handle the files and image and display them. Then we using the butter to connect with the DP0.2 data, and then finally we can focus our attention on the query. We randomly choose a coordinate pair, so array and deck in the simulated LSST sky. And then we choosing a pixelization for the sky. In this case, we change from the the level used in the tutorial notebook that was 10. Here we use 12 because we want to focus on the more smaller image. We want a greater detail, and so we define this pixelization here. Then we define a date, a reference date, and we choose a unit here. That is the minute, and the range of time that we want to use to query for the image. Then we are ready to make the query, where we demanding for all the CalXP image with that pixelization at that point practice, and covered by this time, this range of time. Once obtained this information, this is a record, we save them here, and we obtain a lot of samples since we use, for example, here 4 years, and but we can change these focusing on a smaller fraction of time of simulated for the simulated image. After this, we would like to manage the data that we obtained. So we started declaring some lists, Python lists here, and here we will store the image, the data, and the information about the data for each frames we retrieved. So, for example, the date in a different type, in different format. Sorry. Then we use our coordinates to create a point, and this will be useful for the methods, since these methods, and the following methods will take this as a point, but these methods will not accept the coordinates as a simple float or array and deck. So after made this, we want to extract a fragment, an area from the image, since it was very great, and we want to focus on a small area. So we started defining a region of interest here. Now we use 50 as dimension, and then we, to be honest, here it should be for all the query obtained from the query, but since it took a lot of time, I here put something like 50 records. We asking for the CalXP, the currently CalXP, of course with the right information, and then we define this coordinate, the coordinate of the area that we want to extract from the image, and then we check if the area is contained in the image. Here I create a bounding box where our point is the center of the bounding box, so we can easily check if the polygon contain the data, the coordinates of our point, and then using this simple function that was present in one of the first tutorial, we can extract the patch, the image, saving it in a flattened version in this list with the other information. And then we, as it's possible to see, there is many of these many of these record do not contain the point perfectly. So following this, we define another function here. This function here that is useful for obtaining the element, the date element of the list, and in this way we are able to sort the cutout, so practically all the frame by time. And we made the same thing here, merging the data with the date type, and then finally we are ready to make the interpolation. Since the different times when the images are observed, produce the sequence of image in which we have a sky rotated and translated. So we want to make consistent all the sequence of frame at different time. So we simply here define a grid, a grid of points, and converting in from pixel to sky coordinates, and then we are ready to make these. In practice, we can say here I use this function to make the interpolation, and here is I can explain the arrays, the list. The R_m and the D_m is are the data point coordinates in degree. The A is the data value that we want to interpolate, and the X and Y are the points which to interpolate data. So we use the same data point grid to interpolate the data, and to do so we use a common grid, taking a random image. That is in this case I use the first image of the sequence of the list that has a index corresponding to 0. After this, we finally obtained the interpolated image, and now we start to storage the data, and I will explain later how why we storage in this way the data.
Antonio, can I think I missed something up above. So you defined like an area and a date range, and then you got CalExps for the date range, and then you're making small cutouts of the images.
Yes.
What are the small cutouts? Where are you deciding where to make your small cutouts?
Where are or why I make this? What is the question? Sorry, can you repeat?
Yeah, I think I stopped following somewhere. So you define an area range and a date range, and you got all your CalExps.
Yes, I extract extracting a small fraction of the image. I and save it. I made this to sorry, with a dimension 50 dimension here, and after this I extract a sorry. After this, I made interpolation all the sequence of frames of cutouts. Okay. Firstly, I extract a squared area of 50 points by 50, and then I made the interpolation, and I made so because the interpolation is a lossy function that that in some way include a loss of information. So I start with a greater frame dimension, and then I use the interpolation to map all the area on a smaller grid of 15 by 15 pixels. Okay.
Okay, and then when you say interpolation, are you
Yes.
interpolating in time because you have CalExps at different times? Or are you interpolating in space?
I interpolated the image on a sky coordinates grid. So each image is interpolated on the same grid, but the grid is taken by here, I think, yes. By one of the image of the sequence. So in a consistent way, I guess. And I don't know, do you
Okay,
understand?
okay, keep going. Yeah. Keep
Okay.
going. I think I'll try to pick it up.
Once we make the mapping from the image in the sequence to this smaller grid, interpolating on this point, we now need to storage this data, and to do so we simply use the AstroPy AO fits image, and we store the image in this fits file, and using the header to save information such as the time, the observation time of the image, and the coordinates here. And then of course, I saved all the image in a single sample, in a single folder, and I also saved the image as PNG in a PNG format. Finally, I defined this two function here. Okay, but I using simply function of Linux, the TAR algorithm, I compressed the image in archives, and now I'm ready to download it and moving on another platform. Another thing that I made is this make GIF function that is useful to have a visualization of the sample that we made. And yes, in conclusion, iterating this procedure, we built a great amount of sample where we injected the simulated slow moving object, but this is the workflow. But this is not possible to show here because unfortunately the remaining part of this dataset creation require to use a different hardware. So this is the reason behind the file storage, because once I build all the sample, I download them, and then I move on another machine where I use other information. Briefly, I downloaded all of the Transneptunian object from the JPL database and save all the information of this object on this file, on one of this file, and then I use this information to compute the ephemeris of this object, and then I merge the one single sample with one single object, or in a better way, I use a PSF to draw the object, the ephemeris of the object, into the LSST image. Once this is done, I obtained a single sample of the dataset. Then I repeated the procedure, and I obtained a great dataset to feed my neural network. This is an example, That is a 3D CNN. Since we use a single sample is a 50 frame series of 15 by 15 image. You use a 3D CNN that take care of the third dimension that represent the time. So after we use a lot of technique here. We use L2 regularization and batch normalization, but dropout and 3D max pooling. But the important thing is that after a feature extraction part here, we put the classical fully connected layer to make the net able to discriminate between this sequence where the slow moving object is present or not. And this is it. So I don't know if you have any question. Please tell me.
Thank you. Thanks, Antonio. Round of applause. Okay. So the locations where you were making your cutouts, is that where you like expected the moving object to be? Or you said they were random and then that's where you inject your moving object?
The image that we took are taken randomly in the old the LSST simulated the sky, but the objects are injected in the image in checking if the date of the ephemeris correspond to the date of the time in which the image is observed. So the observed time of one frame should correspond to the ephemeris, the date in which the ephemeris is calculated. And so we made the injection. Okay. I don't know if it's clear.
Yeah. And then the part, oh, actually, are there any other questions? Okay.
Douglas had a question on the chat.
Oh.
You want to know if the notebook is available on DP0 Delegate's contributions GitHub site or elsewhere. He thinks it'd be great to try it out.
Yes. Of course, after the meeting, I will share the notebook with Melissa, and we'll post on the forum of the delegate.
Yeah, and we can try to add it to the delegate contributions repo. Do you know sort of your process here about, it looks like you're making small cutouts and then you have to save them to disk. Do you know sort of about how much space it takes to do it for this much data and how much it'll take in the future?
Fortunately, since the cutout dimension is very small, after I made the frame, the image, I use a compressing algorithm. They don't require a lot. They don't require much space on the disk. But I periodically remove the file because I use it on another machine.
Oh, okay, I see. Okay, Jeff?
Oh, I was just curious. Could you show us what the cutout images look like? I think you had skipped those parts in the.
Yes.
Yeah, I saw you had one there. Cool.
This is of course this is a this is 15 pixel by 15 pixel. Here you can see the date of every single frame. But here I have a more zoom out version. I think. And yes, this object is I don't know if it is clear. Sorry. This object is injected by me in the image. Here I use the 50 by 50 cutout, for example. Okay. And that's something like this. I use another color map here, for example.
I think that that function to create those animated GIFs of a cutout would be really useful for lots of different transients and variables. So
Yeah,
it'll be great if you contribute this to the delegate contributions repo.
no
Thanks.
problem.
Okay, and any other questions? All right, let's thank Antonio again. Well done. Thanks for being here.
Okay, thank you.
Yeah. Okay, and now we switch over to the breakouts part of our delegate assembly, where if anyone wants a breakout room to work on a specific topic with other people who are here, now's the time to suggest it. Oh, my chat went away. It's back. And the main room will, as always, be open for just general Q&A. Is anyone staying for a White Dwarfs room? You got it. Bob, what are you guys working on in there today, in case people want to join?
I've been trying to find the best white dwarf catalogs so I can start modeling using colors to model temperatures and log G and distance.
Okay, like an external catalog of white dwarf physical parameters.
Oh, so I started off using cast jobs and Astrolab and combining Sloan and Gaia data, but I found there's well, actually got help last week. There's a Montreal white dwarf data set and a data set I think out of Germany by Fusillo and a couple other people. I learned how to talk to them, and they look much better than what I've been using.
Okay, cool. All right.
But guidance is always helpful.
Sure, yeah, makes sense. Okay, so one white dwarfs room where anyone's welcome to go and talk about white dwarf catalogs. Anybody else would like a breakout room for today? Ryan.
Yeah, so I guess I'm going to work on like a demo notebook that goes over light curves of like the variable stars or 1A supernovae, like the 07 notebooks. So if there's anyone that is interested in giving feedback on that, that might be good. So maybe like a Jeff, since I would just take pieces of those notebooks to make like a short, demo kind of thing. If this is an appropriate, like a good topic for a breakout, that's what I plan to work on.
Is there anyone here who is new? I think I recognize most names here. But if anyone's like new and you're like really just getting started and you might appreciate a bit of a overview, we can make a breakout room for that. For example, just let me know in the chat or by raising your hand.